Dear children, last class we studied about the Bernoulli's principle and its applications. Today we are going to do some numericals. The first one is water flows through a horizontal pipe whose internal diameter is 2 cm. Note it as d1 equal to 2 cm. Then change it into meter, that is 0.02 meter. Then water flows at a speed of 1 meter per second. So that is V1 equal to 1 meter per second. What should be the diameter of the nozzle? So that you take it as D2, you want to find out. If the water is to emerge at a speed of 4 meter per second. So the speed of water through the nozzle, that is V2 equal to 4 meter per second. So here we can apply the equation of continuity. That is the area of cross section and velocity is different. That is the diameter is different and the velocity is also different. So we can apply the equation of continuity. So what is the equation of continuity? That is the A1 V1 equal to A2 V2. So what is the area of cross section of the pipe? That is the circular cross section. So the area is pi r square. So here the diameter is given. So radius r equal to d by 2. So we can write the area of cross section pi r square equal to pi d by 2 the whole square. That we can apply here. That is the first area A1, that is the pi d1 square by 4 into V1 equal to pi d2 square by 4 into V2. Then pi and pi we can cancel, 4 and 4 we can cancel. Then d2 square, okay, d2 square equal to V1 divided by V2 into d1 square. So substitute the values. What is the V1? 1 divided by V2 4. Then d1, that is the point 0 to the whole square. So we will get the answer d2 equal to 0.01 meter, that is equal to 1 centimeter. Clear? Question number 2. At what velocity does water emerge from an orifice in a tank in which gauge pressure is 3 into 10 raised to 5 Newton per meter square before the flow starts? Density of water 1000 kilogram per meter cube. So here you know that you want to find out the velocity of outflow of liquid from the hole in a tank. There the gauge pressure is given. Its formula is P equal to H rho g. So from that you want to find out H equal to P by rho g. So you substitute the value of pressure, then density, then g, etc. Okay. Then after that you want to find out the velocity of outflow of liquid. What is the formula for the velocity of outflow of liquid? It is equal to the velocity of freely falling body, that is equal to root 2gh. So by substituting the values you will get the answer 24.495 meter per second. Okay. Question number 3. Water is flowing through two horizontal pipes of different diameters which are connected together. In the first pipe, the speed of water is 4 meter per second and the pressure is 2 into 10 raised to 4 Newton per meter square. Calculate the speed and the pressure of water in the second pipe. The diameters of the pipes are 3 centimeter and 6 centimeter respectively. So the diameters of the pipes are given. So you want to find out the radius. So R1 equal to 1.5 centimeter. Change it into meter, and similarly R2 equal to 3 centimeter. Also you change it into meter. Then velocity of the water in the first pipe is given, that is 4 meter per second, and the pressure at the first pipe is also given, that is the V1 and the P1. Then you want to find out the V2 and the P2. So first you want to find out the V2 by applying the equation of continuity. So you know that equation of continuity is A1 V1 equal to A2 V2. So A means it is the area of cross section of the pipe, that is the pi r square. So we can substitute here, that is the pi r1 square V1 equal to pi r2 square V2. Okay. So from this formula you want to find out the V2. So we can write V2 equal to R1 divided by R2 the whole square into V1. Okay. Then by substituting the values R1 equal to 1.5 into 10 raised to minus 2, then R2 and V1. So you will get the answer V2 equal to 1 meter per second. Clear? To find out the pressure, you apply the Bernoulli's theorem for this horizontal flow. So for the horizontal flow, H1 is equal to H2. So we can write the Bernoulli's equation, that is the P1 plus half rho V1 square equal to P2 plus half rho V2 square. Here H1 is equal to H2 because it is the horizontal flow. So from this we can write the P2. P2 equal to P1 plus half rho into this rho, half rho V2 square, take it on the left hand side. So we can write half rho into V1 square minus V2 square. Then apply the pressure P1 that is given in the question. Then density, that is the rho, density of the water, 10 raised to 3 kilogram per meter cube. Then V1 and V2 already given in the question. So after substituting all the values, you will get the answer 2.75 into 10 raised to 4 Newton per meter square. Clear? Next topic we are going to study is viscosity. You know that most of the fluids have some resistance to motion. This resistance to fluid motion is called viscosity. This force exists when there is relative motion between the layers of the liquid. So we can define viscosity is the property of fluid by virtue of which an internal force of friction comes into play when a fluid is in motion and which opposes the relative motion between its different layers. The backward dragging force called viscous force. Okay. What are the examples of viscosity? When we swim in a pool of water, we experience some resistance to our motion. This is due to viscous force. Then second example, the cloud particles fall down very slowly on account of viscosity of air and hence it can be seen floating in the sky. Third one example, we can walk fast in air but not in water. You know that. This is because of viscosity of air, which is smaller than that of water. Okay, viscosity of air is much smaller than that of water. That means water is more viscous than air. Clear? What is the cause of viscous force? So you imagine that when a boat moves on the surface of water, the upper layers of the fluid moves along with the boat. When we go deeper, the movement of particles reduces and there is attraction between the molecules. So, deeper molecules try to prevent the surface particles to move with the boat. Thus, force which prevents the relative motion of particles on the surface, that is called the viscous force. Here, the upper layers moves forward and lower layer pulls it backward. This results in force between the layers called viscous force. Okay. And this type of flow is called the laminar flow. Then another one point that the fluid in contact with a surface has the same velocity as that of the surface. So, the layer of the liquid in contact with fixed surface is stationary. The layers of velocity, that is the velocity of layers, increase uniformly from bottom to the top. Bottom layer is so here when you look at this figure, this bottom layer is fixed. So the liquid which is in contact with this bottom layer has the velocity 0. Then when the liquid moves on the top layer, moves with a velocity v. So here the velocity is increasing from bottom to the top. Okay. when a fluid flows through a pipe. So this figure represents the fluid flows through a pipe. So when a fluid is flowing in a pipe or a tube, then velocity of liquid layer along the axis of the tube is maximum and decreases gradually as we move towards the walls, and it becomes zero because that means the walls of the pipe is stationary. So the velocity of the liquid layer which is in contact with the walls is stationary, that is zero, its velocity is zero, but the velocity of the fluid moves along the axis of the pipe is maximum. Okay, so this is a viscous fluid which is flowing through the pipe. Okay, here the figure shows a liquid layer between two parallel glass plates, in which the lower plate is fixed and the upper one is moving with a velocity v. So you consider a portion of the liquid A, B, C, D. When you apply a force F, this portion of the liquid moves through a displacement delta x in a short interval of time delta t. During this time interval, the liquid undergone a shear strain, a shearing strain. That is, the liquid moves away from its original position and it attains a shape A, E, F, D. So this displacement is known as the shearing strain. That is, it moved away from its original position. So this shearing strain is noted as theta. Okay, this shearing strain is noted as theta. So this shearing strain is the ratio of, so we can write it as tan theta. If you consider this as a triangle, so we can consider that is a tan theta equal to this shearing strain is the ratio, it is defined as the ratio of relative displacement to the length. So here the distance between the two plates, that is noted as L. So this shearing strain is defined as the ratio of relative displacement delta x to the length, that is tan theta equal to delta x by L. So if theta is very small, then tan theta is approximately equal to theta. So we can write shearing strain theta equal to delta x by L. So when the liquid flows, shearing strain also increases with the time continuously. So we can say that this shearing strain as the rate of change of strain, or we can say that strain rate, because the strain rate, that is shearing strain, increases when the liquid flows. Shearing strain increases with the time continuously when the liquid flows. So this shearing strain is known as the rate of change of strain or strain rate. Clear? So that strain rate we can write strain rate. Strain rate equal to, what is the shearing strain here? That is delta x by L divided by delta t. So shearing strain with respect to the time. This is the strain rate. So we can write delta x by L delta t. So this is the strain rate or rate of change of strain. So we can define a term coefficient of viscosity eta. So coefficient of viscosity eta is equal to the ratio of shearing stress. Shearing stress is represented by F by A. Clear? Shearing stress to the strain rate. Shearing stress to the strain rate, that is delta x by L delta x by L delta t. Clear? So coefficient of viscosity is defined as shearing stress to the strain rate. So that we can write here, that is F by A divided by what is delta x by delta t, that is equal to V. So we can write here, that is V by L. So coefficient of viscosity eta equal to FL divided by VA. Okay, so here L comes to the numerator. So we can write FL by VA. So coefficient of viscosity is defined as, it is pronounced by eta. It is represented by eta. Eta. So coefficient of viscosity eta is defined as the ratio of shearing stress to the shearing strain. Then what is the unit of this coefficient of viscosity? So it is noted as Poiseuille. Unit of viscosity is Poiseuille. Okay. So it is represented, its unit is Poiseuille and it is represented by PL. Okay, capital letter P and small letter L. Its unit is Poiseuille. So we can write some other units like this using this formula. That is, what is the unit of force? That is the Newton. And what is the unit of L length? That is meter, divided by velocity meter per second and area meter square. So this meter and meter we can cancel. Then we can write to Newton second meter raised to minus 2. Or we can write Newton per meter square, that is a Pascal. Pascal second. So these are other two units of coefficient of viscosity, but the SI unit of coefficient of viscosity is Poiseuille. Clear? Then what is the dimension? So after substituting the dimension of F, L and VA, we get the dimension, that is M L raised to minus 1 T raised to minus 1. This is the dimension of coefficient of viscosity. Clear? So you studied the coefficient of viscosity. It is the ratio of shearing stress to the strain rate. That is, when you apply a force on a liquid, here the liquid is applied between the two glass plates. The bottom glass plate is stationary and the upper glass plate is movable. So you are applying a liquid, for example oil. Then you apply a force. Then the liquid or the plate moves through a displacement delta x. Then instead of the oil, you apply some honey. Then to move the plate through this displacement or to move the liquid through this displacement, you have to apply a greater force because honey is more viscous than oil. So, the coefficient of viscosity is different for different liquid, but it is a constant value. Okay, but it is a constant. It is different for different liquid, but it is a constant. So, viscosity of most of the liquids are shown in your or given in your textbook. You go through it. Okay. So, that is the coefficient of viscosity. Clear? It is a constant value, but it is different for different liquid. Okay. Some other points about this viscosity. Some liquids, that is the thin liquids like water, alcohol, they are the less viscous liquids. But some thick liquids, coal tar, blood, glycerin, they are more viscous. Okay. So, likewise, we can classify the liquids into less viscous liquids and more viscous liquids, etc. And one more point about this viscosity. The viscosity of liquids decreases with the temperature. That is, when you heat the liquid, viscosity decreases. That is, the friction between the layers decreases. But in the case of gases, it increases. So when you increase the temperature of the gases, it's a friction. Okay, the friction between the layers increases. So viscosity of liquids decreases with the temperature while it increases in the case of gases. Clear? Stokes law. So what is meant by Stokes law? So here, when a body falls through a viscous fluid. So here this vessel contains the viscous fluid. So when a body falls through this viscous fluid, the layer of the fluid in contact with this body moves with its velocity. But the fluid away from, that means the fluid layer away from this moving body is remains at rest. This produces the relative motion between the different layers of the liquid. Okay, as a result, what happens? The body experiences a viscous force. This tends to retard its motion. This retarding force, F, increases with the increasing velocity of the body. That is, velocity of the body increases, then retarding force also increases. So, this viscous force depends on the coefficient of viscosity of the fluid, then radius of the spherical body. When the radius of the spherical body increases, then viscous force also increases. Then coefficient of viscosity increases, then viscous force also increases. Then velocity of the body increases, then viscous force also increases. So that is the Stokes law. So we can say that the backward viscous force acting on a small spherical body of radius r moving with uniform velocity v through fluid of viscosity eta is given by F equal to 6 pi eta Rv. 6 pi is a constant. So the viscous force is directly proportional to coefficient of viscosity, then radius of the spherical body and velocity of the body. So this 6 pi is a constant. Okay, so that is known as the Stokes law. Stokes law derived by the scientist Sir George G. Stokes, an English scientist. So it is known as the Stokes law.